Okay, so Exponent Rules Recap. So what should we know and what will be on the final? Well, everything we've learned will be on the final, but just some recap real quick. These should be in your notes, but you should know the product rule, right? Which is just anything x to the n power times x to the m power equals x to the n plus m, right? So such as an example would be 2 to the second power times 2 to the fourth power would be 2 to the 2 plus 4, right? We add the exponents, so 2 to the 6. Now, this gets confusing when we combine many situations together, so we'll just go through them one at a time, and we'll start with the next one being quotient rule. And this won't go too long, but quotient rule is just kind of similar. It's x to the n over x to the m is equal to x to the n minus m. And you can use any variables as long as the bases are the same for right now, and there are rules we've come to understand what happens if bases are different. But example would be, we'll call that example 1, but example 1 here would be x to the, well, it's not x, I guess I could use x, but I'll use a number, it doesn't matter. 3 to the 7th over 3 to the 2nd is equal to 3 to the 7 minus 2, or 3 to the 5th. Remember, there's 7 3's in the top, 2 3's in the bottom, so, but just by our division rule, I would cancel out 2, since they share 2, and left over with 5. Then there's raising a power to a power, and that is when we have parentheses. So if I have x to the m and I raise it to the n, notice there's parentheses here where the product rule there is no parentheses, even though we think of parentheses as product when we are dealing with certain things, but not between the what's outside and inside so much, but yes, because we're going to distribute, we get x to the m times n, and that's it. So example, again, we'll put an example, 3 to the 3rd raised to the 7th is 3 to the 21st. Now, our calculators can figure out what all of that is, but we're not going to worry about that right now. These are just recapping. Then there's the 0 power rule. That is anything to the 0 power, right? X to the 0 power is 1. Anything to the 0 power is 1. So example, we'll look at an example. So if I have 3 to the 0 power equals 1. Now, it is important that I put parentheses around it, because I'm going to show you example 2, where a lot of people still kind of make these slight errors. If I say negative 3 to the 0 power, that's negative 1. Again, just a reminder, the 0 is only applied to the 3 here, whereas the 0 would be applied to the 3. And if there was a negative sign inside the parentheses, that would still be 1. And I'll just clean that up, make it look a bit neater. So whether it's 3 or negative 3 inside the parentheses, it's 1. But when the 0 is not accompanied by that parentheses, which here kind of gives us that idea that if there was a negative in front of the exponent in this rule here or here, right, then this would get the effect of the distribution, whereas down here it does not. And then the last one is the negative exponent rule, which we have gone through this in good detail if you have your notes, but negative rule for exponents is if I have x to the, say, negative n, exponent is 1 over x to the n. And we kind of looked at the reasons for this through the quotient rule. So if you have notes from back in January, you can kind of go back and look through that reasoning. I will recap it in class, but I just am going through quickly some general rules. So if I have, say, for instance, example, x, I don't know, so we'll say 3 to the negative 2nd power, that's just 1 over 3 to the 2nd power, but if it says to simplify, it's 1/9, right? So those two things are equivalent. You should be able to handle that. So let's kind of look at some slightly more challenging each situation. So if I said, here's one, x to the third, y to the fourth, times x to the seventh, y to the eighth. Well, just following our rule, the bases with the exponents, since we're multiplying, I can add the exponents. That is x to the 10th, y to the 12th, right? And likewise, I can kind of look at, this is quotient, that was product rule. Now with the quotient rule, I can kind of do the same thing. I could say x to the third, y to the fourth, over x to the seventh, y to the eighth. Well, this is going to lead us into some negative exponents as well, because this one, right, we said up here, we said x to the 3 plus 7 times y to the 4 plus 8, and we get 10 and 12. Here we're going to have y to the, x to the 3 minus 7. And of course, and then y to the 4 minus 8. Of course, you need to know your negative exponents, but that's just x to the negative 4th and y to the negative 4th. And we don't like to leave things with negative exponents, so you should recognize that that just becomes 1 over x to the 4th, y to the 4th, because they're both negative. Of course, if the negative exponents were in the denominator, then it would come to the top and become positive. And another example, let's say I have 3 to the third raised to the second power, right? Well, that's really the same thing as this. But what if I have 3x to the y, and I put a 2 exponent for the x and a 3 exponent for the y? This is where a lot of people kind of forget that this 2 gets distributed to all the exponents. So I'd have 3 squared x to the 4th, and we distribute it through multiplication, not addition. And so I do simplify it one step further because I want to simplify that 3 squared. And that is the another example for raising power to a power. And of course, the zero exponent rule is as long as everything is in exponents, it doesn't matter what's in here. It could be x squared, y to the third, z to the 4th, q, whatever. All of this equals 1. Anything inside that parentheses. It could be negative, it could be over fraction, yada, yada, yada. All right, and negative exponent rules get a little tricky because, well, just I'll do 2 examples. If I have, say, 2 to the negative third, that is 1 over 2 to the third, which, of course, is 1 over 8. But what if I have a different example? What if I have 1 over, I'll use a different number, 1 over 4 to the negative third? That just becomes 4 to the third, right? Basically, we flip it upside down and the negative sign disappears. But where this gets a little tricky is when we have multiple things happening in a problem. So let's say I have x to the negative 4th, y to the negative 3rd over z to the negative 2nd. Well, whatever's got the negative exponent on top, right, they go to the bottom and they become positive. And whatever's got the negative exponent on the bottom goes to the top and becomes positive. That's pretty much that simple. Now you do still have to combine like variables in terms and combine them properly. So that is exponent rules recapped relatively quickly. So we're going to look at rational exponents and radicals, rational exponents and radicals. And this should be also pretty straightforward, and we can do some examples together right now. But rational exponents are just looking at if I have a fractional exponent. So like, let's say I have x to the 1, we'll say 2/3 power, right? So what does that mean? It means that I have to recall that the base right here, this is the base, and we have a fractional exponent with a power as the numerator and a root as the denominator. So if I want to put it into radical form, well, I just take the base, and the base goes here. And the power would be up here, right? I'm going to put it in parentheses just because. And the root would be here. Goes in this location. And we know that we can rewrite that as the base is here, and we're looking for the third root. And I don't know, maybe that's a 7, and then so I'm going to raise it to the 7th power. So it's just rewriting it. These two things are equivalent forms, okay? They're just written in different ways because they can give us different ways of simplifying processes. So if I have, here's one that we've done in the past, 81 over 256, raised to the 1/8 power, times 81 over 256 raised to the 5/6 power. Well, notice if I want to do something to this one where I have combined like things, right? I notice that the exponents have, oh, sorry, this should be an 8, not 1/5/6. I apologize, but both have the same exponent bases, so that, or for denominator, so that we can just combine them, because our product rule tells us to add the exponents. So 1/8 plus 5/8. So that's 81 to the 6/8 over 256 to the 6/8. Now, notice I didn't put 1/8 in the numerator and denominator and do numerator and denominator on both of these, but the parentheses implies that you would distribute to both. But I can work faster if I just simplify it to one term before I do that. And I didn't really have to do that because, in fact, 6/8 simplifies to 3/4. So I'm just showing you the whole procedure of movements. Of course, once you know this, you'll go through it much faster in organization. But then I'm going to go back and look at my bases. I can put 81 here and 256 here. And then my root is 4 and my exponent is 3. Now, you'd still need to remember how to use the calculator to solve this. And just as a general reminder, to use the calculator, you do need to use this second function and the YX button. So if I type in 81 into the calculator, I use second function, YX, and then the root is 4. So 4. Look at that, I get 3. So this is now 3 to the 3rd power, and I can do the same thing for 256, and I know that's to the 4th root of 256 is 4, and then I raise it to the 3rd power. And then to raise to the 3rd power, you do not hit the green, you just hit YX. And you hit the exponent you look for. And so 4 to the 3rd power is 64, and 3 to the 3rd power is just 27, and you can verify that by hitting 3 to the 3rd power, and it's 27. So that is rational exponents and radicals. And of course, combining radicals, adding them, let's say I add radicals or multiply them, you could have 3 square roots of 3 plus 5 square roots of 3. You add the coefficients. That would be 8 square roots of 3. Now, where this gets a little tricky is you have to simplify radicals if they are not the same bases. So, for instance, example that would look like that would be, let's say I have 4 square roots of 6 plus, I don't know, we'll say 2 square roots of 24. Well, notice that these aren't the same basis, so I cannot add these, the 4 and the 2, which are like coefficients. But if I factor this and I pull out a perfect square, I know 4 times 6 is 24, but I keep my radical symbol there. Now, others will suggest that you do it a different way, but this is how I'm suggesting you do it. So to finish, we take the square root of 4. We have 2 times 2 on the square root of 6. And then we still have this 4 square roots of 6. We'll pull it all the way up here. So I have 4 square roots of 6 on the first term. Now 2 times 2 is 4 plus 4 square roots of 6, which gives us 8 square roots of 6. So you do need to remember your perfect squares. Of course, I'll list them real fast. 1, 4, 9, 16, 25, 36, 64, but I did skip 49, 81, and 100. And then there's more. Your job will be to know all of them. And then, of course, these are perfect squares. And then you need perfect cubes, right? So 1, 8, 27, 64, and 125. This is 1 times 1 times 1, or 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed. They are all the equivalent forms. And your job is to know all of this, and that will help you with the assignment.